Hey guys, it's Knock Me here. Today we're going to continue where we left off and do a couple more examples of calculating volume using definite integrals, looking at cross sections of these shapes, okay? So this problem right here is going to be looking at the volume of a solid that is bounded by these four equations. Y is equal to the square root of x plus 2, y is equal to negative x cubed, x is equal to 0, and x is equal to 9, with the cross sections that are semicircles. Semicircles this time, right? So first thing I'm going to do is go ahead and graph this out, right? I'm just going to do a quick sketch right here. So let's see here. Y is equal to square root of x is something that looks something like this, except it's square root of x plus 2. I'm going to go ahead and move that up. So this is going to look something like here. Let's pretend that this is 2. It's going to go something like that, right? The next curve we have is y is equal to negative x cubed. Y is equal to negative x cubed is a cubic, but it's switched now. It's going this way now because it's negative, so it's going something like that, right? Pretend that that's drawn. You know what? Let me just do that again. It's something like that, let's say, right? And then we have our x equals, which are vertical lines at x equals 0 and x equals 9, right? X equals 0 and x equals 9. So it looks like our integral is going to go from 0 to 9, right? Getting this as our base, right, for our three-dimensional shape. And it's popping out of this, forming semicircles. So let me draw this as our base for our three-dimensional shape. So I'll go ahead and let's go ahead and make our base here. It's going to look something like this, and it's going to go something like that. And there's our x-axis, there's our y-axis. So our square root of x plus 2 function would look something like this, going that way, right? And our negative x cubed will probably look something like that, right? And then we have our x equals to 0 and x equals to 9. X equals to 9, right? That's not going the way I want it to go. Hold up here a second. Let's try that one more time. Let's see here. Let's see here. It's going to look something more like this, I would say. No, still not right. There we go. That's better. That's better. Right? X equals 9. Okay? And again, this is our base right here going this way, perpendicular to the x-axis. So it's doing that here, it's doing that there, and it's doing that all the way down here as well. And they're making semicircles, which are half circles, from here to here, and from here to here. So that's what our shape is going to look like right here. It's this guy right, that pretend that reached all the way down there, all the way down here, right? Horrible drawing, but it's okay. You guys kind of get the idea, hopefully, right? So we have our shape here, this semicircle. It looks something like this, okay? And the base of that semicircle has these as our points, right? We have this over here, which is going to be defined by the square root of x plus 2, and then we have the other one down here, which is defined by negative x cubed, okay? Now, how do we calculate the area of a semicircle, right? Well, it's just half a circle. So if I have a circle, which is area is equal to pi r squared, a semicircle would just be half of that. So we just take, this would be 1/2 pi r squared, and that would help me calculate the area of the semicircle. So looking at this, though, I don't really have an easy way to calculate r. I do have a way to calculate the diameter, though. The diameter of the circle, or the semicircle, is going to be equal to, it looks like the square root of x plus 2 minus negative x cubed. And that's what the diameter is equal to, right? And the radius is just going to be equal to half of that, right? The radius is equal to 1/2 square root of x plus 2. Negative and a negative makes a positive x cubed. That's what my radius is. Okay, so if I'm looking to calculate the area of the semicircle, right, the area of the semicircle is just going to equal 1/2 pi r squared, where our r is just going to be replaced with that. So I have here 1/2 pi times 1/2 of this function right here, x squared plus 2 plus x cubed. But of course, this whole thing is being squared. Okay? And that will help us calculate the area of the semicircle, right? All the way across from beginning at x equals 0, x equals to whatever this is, and x equals to 9. We're going to do this all the way through. Okay? And each of these are going to have a thickness of about, I don't know, dx, let's say, right? A small thickness there. And when we multiply by that thickness, that will turn this area into a volume of this chunk that's in between 0 to 9. And if I'm looking for the total volume from 0 to 9, all I have to do then is just integrate this thing, right? Just like we've done in the previous problems from 0 to 9. And that is it. That would help us calculate the volume of this solid that has cross sections that are semicircles. You guys starting to catch on about these problems here? It's pretty much the same idea. We're looking to calculate the area, right, of your base, right? The area of a specific shape that is perpendicular to your base, right? And using the functions that form your base, right, plugged in there, that will help you start off to find that area. Multiply that area by the thickness of it, this dx, and then just sum it from start to finish, right? And that will give you the total volume of the solid that you have drawn there, okay? I don't know what the name of this solid is. I'm pretty sure it has a name, but I don't actually know. Looks kind of like an amphitheater, right? Anyways, for something like this one, you could FOIL it out, but I'd rather not. Go ahead and going to plug this into the calculator and see what we get. And this is where we got to be really careful, right, when we're plugging into our calculator. If we can turn on the calculator. Come on. Let's try this again. Come on, calculator, turn on. There we go. There we go. Okay, so we're going to go ahead and plug this in. Of course, it's under math, option 9, right? And this integral is going to go from 0 to 9. 0 to 9. And the function I have in here is going to be, let's put this carefully now, it's going to be 1/2, right, times pi times, all right, let's do this carefully, 1/2 multiplied by the square root of x plus 2 plus x cubed. Close that one off. Close, and that's there. I'm going to close that one off, and we're going to square this whole thing. And that should be it. All right, that's the whole radius in there being squared multiplied by pi and another 1/2. And we'll go ahead and calculate that. That's going to give us a volume of, taking a second here, volume of 274,394 cubic units, right? Units cubed, however you want to say. All right, and it kind of makes sense that it's very, very large. Some of you guys might not realize this, but I drew this not to scale. This part down here where it's crossing at x equals 9 and the graph y is equal to negative x cubed, right? Think about that. The number that's being plugged in for x right there, so that those points equal, gives you a y output value of 9 cubed, right? Negative 9 cubed, which is going to be negative whatever 81 times 9 is. 729, negative 729. That's the that would be the that would be the y value, and the top value up there would be, what was it? I think like 5. So that distance, that diameter at the very last circle, on this very last one over here, would be somewhere along the lines of 734 or something like that as your diameter, right? So then when you calculate that area, it's going to be very large. But yeah, that's the That's this problem right here, right? And again, it seems overly simple, but it's a really big concept that you need to grasp, right? What you're doing for these problems is you're trying to figure out your region R, and that's going to be your base of your three-dimensional shape, right? Once you figure out that is your base of your three-dimensional shape, right, which is these guys all the way along down here, the shape that's popping out of that base, right, will be given to you, whether it be a semicircle, a square, a quarter circle, right, or an isosceles triangle, all that stuff, they'll give you that. And then you calculate the area of each of those pieces that are popping out, right, multiply it by its thickness of dx, and then integrate it from start to finish. Okay? I'm going to do one more problem today. Let's see here. And this one's going to be a little bit more complicated. Right? Let's take a look here. Find the volume of a solid bounded by y is equal to x squared minus 4x and y is equal to 8x minus 2x squared with cross sections that are your guys' favorite trapezoids, right? With the top base equaling to 1/2 the bottom base and the height equaling to 3/5 of the bottom base. Not only is it your favorite shape, but we also have ratios with fractions involved now, right? For the height of the trapezoid and the top base compared to the bottom base. Fun stuff, guys, fun stuff. Let's take a look here. All right, so I'm gonna go ahead and graph this out, okay? Y is equal to x squared minus 4x is going to look something like this. Whoops, no. Something like this. And I should have did that in another color. Let's make that red. Let's say, like, how am I missing this? It's gonna look something like that. And then y is equal to 8x minus 2x squared is gonna look something like this. There we go. Two parabolas forming a bounded region now from some number over here to some number over there. So I'm actually gonna have to do a little bit of algebra here. I need to calculate what those intersections are, right? So I know where to integrate from and to. Okay? In order to do that, I just set the two equations equal to each other. I have here x squared minus 4x is equal to 8x minus 2x squared. And this is a nice quadratic to solve, right? If you remember, to solve quadratics, first step we can do is set it equal to 0, move all the x terms over to one side. I'm going to move everything to the left-hand side over here, so I'm going to add the 2x squared over, so I get 3x squared. Move the 8x over, it's going to be negative 12x equals to 0, right? You could do the quadratic formula, but it looks like this is factorable. I get a common factor of 3x out, and I have here x minus 4 is equal to 0, so my points are going to be x is equal to 0 and x is equal to 4. That helps me out a lot, actually. That tells me that that's crossing at x equals 0 and that's crossing at x equals 4. Okay? Now, that just involved us to do a little bit more math to calculate those endpoints, but that tells me, though, when I do my integral, right, I'm going to go from x equals 0 to x equals 4. Right? My base is still this right here. This is my base right here. Okay? I'm going to go ahead and draw this three-dimensionally, and the area that is popping out of this base is going to be a trapezoid. So let's go ahead and draw this over here. Let's see here. All right, here we go. I'm going to try my best here. Right? So first of all, we have y is equal to x squared minus 4x. It's going to look something like this. Right? Something like that. Crossing at x equals 0 and x equals 4. And then the other one is 8x minus 2x squared, which is going to look something like that. Right? Whew. Okay. Again, crossing at 0 and x equals 4. Right? Let's turn it on its side. And we're going to have here, basically, that's my base of my trapezoids. Right? And I'm going to have another one here, and I'm going to have another one here, and infinitely many along the way. But I'm going to go ahead and draw this like so. So this is popping up out of this thing like so, and it's popping out like that here. Whoop. Let's try that again. There we go. And like so. See that? Let's see here. Something like this, like that, and like that. pretend that I got that drawn well there, right? And those are the trapezoids that are popping out there with the base here and another base there, okay? So if I'm looking at this, I'm trying to calculate the area of this trapezoid. It should look something like this, right? Where I have base 1, base 2, and the height. And you guys, of course, remember, right, when we first started this using the trapezoid rule, we've hopefully learned the area of a trapezoid is very simple. It's just 1/2 base 1 plus base 2, times the height, right? And that's pretty much it. But now we just got to go in there and figure out what the heck is base 1 and what the heck is base 2 and what the heck is the height, right? Base 1 looks like it's the blue function minus the red function, which in this case is 8x minus 2x squared. So that's over here. 8x minus 2x squared, right? And this is going to be subtracting from the bottom function, which is the red function, which is going to be x squared minus 4x, right? Let's go ahead and simplify this so we don't have to look at this crazy thing and write this over and over again. Negative 2x squared minus x squared is going to give me a negative 3x squared. And 8x minus a negative 4x is going to give me a positive 12x, right? So that's what base 1 is equal to. Base 1 is equal to negative 3x squared plus 12x, okay? And that means base 2 is related to that in the fact that it is 1/2 of that, right? So base 2 is equal to 1/2 of whatever base 1 is, okay? And the height is equal to 3/5 of the bottom base. So it's equal to 3/5 times base 1, right? So we have all this information now. We're going to go ahead and calculate the area of one of these trapezoids that is cut into this shape, okay? Let's go ahead and do that real quick. I'm going to go ahead and scroll down here so I can get a little bit more space. And we're going to see that the area, right, the area, I don't need to write that out. The area is already written up there, is equal to 1/2 base 1, which is going to be negative 3x squared plus 12x, plus base 2, which is going to be equal to 1/2 base 1. So 1/2 times negative 3x squared plus 12x, right? So that's right here. This is base 1 and this is base 2, right? And this is all going to be multiplied by the height. I'm running out of space over here. Let me scroll this over here real quick. Oh, sorry. And the height is equal to 3/5 times negative 3x squared plus 12x. There we go. This whole thing right here, by the way, this is the height. So this is my h, this is my base 2, and this is my base 1, right? And this whole thing that we just found, or just wrote out, this is the area of a single trapezoid, right? Area of a single trapezoid for this cutoff that we have for this shape up here, right there, right? It's just one of them. And we're going to do this infinitely many times, right? Of course, though, I want to do the volume of these things, and the volume needs to include the thickness of each of these pieces. And the thickness here is going to be this dx, right? That dx. So we're going to multiply this whole area piece by how thick it is, which is this dx right here. When you multiply that to this entire area function, right? And that'll give me the volume of one of these pieces. Now, if I want to do the volume of the entire solid, it's going to be from beginning, which it looks like it was crossing at 0, all the way to the end, which is 4. So if I do the integral from 0 to 4 of this thing here, it'll give me the volume of the shape that's drawn up there. I did not actually finish the 3D drawing because I don't think I can actually. I'll try, you know. I'll try to draw it out for you guys. So it's going to look something like, of course, that's going to be the base all the way to here. And then the top part is going to look something like that. Oops, missed. It's going to look something like right there. It's going to look something like this, all the way to there. And this is going to come out here and come back to here. Huh. I don't know how to describe what that shape is. It's like an oval and kind of like pointed edges on the top, and the top part should be like not flat. It should actually be higher because the height is 3/5 of the base. So I didn't draw that too well. It should be like more going up more in the middle here, something like that. Well, good luck trying to imagine that out. But anyways, you could probably multiply this out. It doesn't look too complicated. You could do this one by hand. If this was on an AP exam, this could be one of the non-calculated questions. You could do this. You could do this integral. You just have to do some algebra involved there and then get it into something that you could do the power rule with. All right. I'm not going to go ahead and calculate this. I'm going to let you guys figure this one out. I'll have another example for today as well. You're going to need to practice these, right? All kinds of shapes and sizes will come along, whether it be a square, trapezoids, semicircles, even circles could be thrown in there. You got to be ready for all of those. All right, so I'm going to have a couple examples for this as well. So go ahead and practice. If you don't know how to do it, please stop by during my office hours. It's set to 9 to 10, but again, if you need to do an afternoon time, I can as well. I should be available up until 3. Just message me on Remind, let me know, and I'll get on there for you, okay? All right, with that said, hope you guys are doing okay. I really do miss all of you. Hopefully everything's going okay with you guys. Everything's fine on my end. I honestly just miss seeing your faces, okay? I'll talk to you later, okay? Have a good one. Bye.